Good evening all of you, and here is the discussion on mean value theorem 2. You can see the playlist of differential calculus for mean value theorem 1. There I have discussed many problems. Since this problem was already asked in J8 once and the solutions which is available still after 4 years is not very rigorous. So that's why I wanted to make a video on this. So the question is for every twice differentiable function f defined from R to minus 2 to 2 with f of 0 whole square plus f dash 0 whole square equals 85. Which of the following statement is correct? Remember, the function characteristics is given as twice differentiable, and this is very important. As you can see the problem on the thumb screen. So the first option was there exists some r comma s belongs to real number such that r is less than s, such that f is 1 1 on the open interval r to s. Right? And this was for first part of the problem. The second part of the problem was there exists some x naught belonging to minus 4 to 0 such that mod of f dash x naught is less than equal to 1. And third part of the problem was limit x tends to infinity equals 1. So actually we have to check which of the following is true. Okay, so mostly they are asking about existence of the statements. And fourth one was there exists some alpha belonging to minus 4 to 4 such that f of alpha plus f double dash alpha equals 0 and f dash alpha is not equal to 0. Okay, so this is in fact the toughest problem from JEE Advanced 2018. So let's see how to go about this. Usually the explanation which is given for the first part in most of the coaching institute is, since f of x cannot be constant, because let's say if f of x is constant, some c, then f dash x is going to be 0. Right? And since f dash x is 0, so that will force f0 whole square plus f dash 0 whole square equals 85 will be ambiguous. The reason being this quantity will be 0, so f0 has to be plus minus 85, which is anyway not possible because the codomain of function is minus 2 to 2, which forces function to lie between minus 2 to 2. So we already know no matter what input you keep, the function is definitely dancing from minus 2 to 2. So this is a variable of 2, this is minus 2, and my function can be like this, whatever it does, it is bounded from minus 2 to 2. Right? And hence they are taking 1 as the option. Now in fact this is conceptually wrong. Why? Because if a function is not constant, it does not guarantee it has to be 1 1 as of now, because function might do oscillation. It might do very serious and crazy kind of oscillation. Right? Okay, so basically what they are missing is this twice differentiability is very important and very strong condition which is imposed in the problem. The direct consequence of this goes to option A. Okay, so the credit for option A is not just constancy will violate it, because if a function is not constant, it means in some interval it has to be 1 1. Directly you can't conclude because the information given was only at around 0. Okay, so the reason is twice differentiability. See how. And what exactly first twice differentiability means? Twice differentiability means the function f of x should be differentiable. It means f dash x should exist. And f dash x existence should also be such that f dash x is also continuous as well as f dash x is differentiable, which means f double dash x exists. Okay, at each and every point in the domain. It means twice differentiability means existence of continuity and differentiability of f of x. Existence of continuity and differentiability of f dash of x. So f dash x should also be differentiable, and hence by default it should be continuous. Now how that continuity of f dash guarantees this? Suppose if I take a function f of x equals x squared sine 1 by x for x not equal to 0 and is 0 for, let's say, x equal to 0. Now clearly you can see the function is continuous at x equal to 0 because it will go to 0 into something finite dancing from minus 1 to 1. Is it differentiable at x equal to 0? Let's use a definition. First principle, limit x tends to 0, fx minus f0, that will give x squared sine 1 over x divided by x minus 0. X cancel. Now definitely this limit exists. Either you can use sandwich theorem or whatever, and this is 0. It means I can tell f dash 0 exists, and that's 0. Right? Now is f dash continuous at x equal to 0? So let's check it. So at x not equal to 0, I can definitely find its derivative. So that will give 2x sine 1 by x. Derivative of sine 1 by x is cos 1 by x. Into that's minus 1 by x square into x square. So this is derivative x not equal to 0. Now I know f dash x at 0, it will give 0 as the answer. Now let's see what happens in the vicinity of 0. So if we'll try to find limit x tends to, let's say, 0 plus of this expression. So clearly you can see x square gets cancelled because it's not exactly 0, and we have 2x sine 1 over x plus cos 1 by x into minus 1. Now when x is limit x tends to 0 plus, this is going to be finite. Not only finite, but this is 0 because 0 into something finite dancing from minus 1 to 1. Sine infinity will dance from minus 1 to 1. So this will go to 0, this limit. Now this quantity will oscillate from minus 1 to plus 1. So you can clearly see limit x tends to 0 plus doesn't exist because it will just have oscillation behavior. Similarly at 0 minus it will have oscillation behavior. But what's important, at x equal to 0, the slope of the function dies exactly. It means f dash 0 is 0. But f dash 0 0 does not means in the nearby vicinity the function was increasing and before that it was. So let's say at x equal to 0, it does not means between 0 to some number ipsa, where ipsa is a positive quantity and it's too small, the function is increasing, and minus ipsa to 0, function was decreasing. It doesn't mean at all. Or neither it means like point x equal to 0 is a point of mean and maxima. Here what you can see is after 0 the function is oscillating like anything. Right. So around 0, no matter how close interval I take, around 0, no matter how close interval I take, we can't comment, or in fact we can definitely tell that the function is having oscillated behavior. So although f dash 0 exists, but f dash 0 plus, f dash 0 minus doesn't exist. So hence this is a discontinuous derivative at 0. So all the function is continuous at x equal to 0, function is differentiable at x equal to 0, but f dash is not continuous at x equal to 0. It means this function is not twice differentiable. Right? So this is one of the very serious thing that you have to take care of. So just because at some point, let's say if f dash 0 becomes 1, immediately don't conclude that in the near vicinity of 0 the function is strictly increasing, because at 0 means the slope is positive. It might happen f dash 0 is 1, but the function is oscillating like this. Okay, and definitely you can give many examples like the way I have given. So in that sense, I defend the reasoning like just because you showed for constancy, it does not guarantee like it's 1. So what guarantees 1 since the function is twice differentiable? So now using mean value theorem, I can give a guarantee there exists an interval around 0 such that it must be 1. The reason being means now it's twice differentiable, and at 0 what information I am getting? At 0 I am getting information of clearly f dash 0 is non-zero. Why? Because f0 bound will be, this will be less than equal to 2 according to codomain restriction. So f0 square will be less than equal to 4. So the maximum value of f0 square will be 4. It means f dash whole square will be 85 minus 4. So it will definitely be less than equal to that value. It means I know f dash 0 whole square will be less than equal to 81, right? So f dash, when f0 will go to maximum, f dash 0 will go to its minimum. So at when it is 4, the value that I'll get at f dash is root 81, right? So which is 9. So clearly which is not 0. So no matter what value of f of 0 I take, f dash 0 is not going to be 0 in any of this interval because of this equality, right? Because of this equality. So hence I can tell, since at any point f dash 0 is non-zero, so if I take a vicinity, if I take a small vicinity of that, it might be symmetric vicinity or not symmetric, let's say minus delta to delta, and if I apply mean value theorem in this interval, so I can tell f of delta minus f of minus delta divided by 2 delta is some f dash zeta, right? And in this interval at exactly at 0, its derivative is non-zero, right? And there is no oscillation behavior because it's twice differentiable. It means the derivative is also continuous at that point. And since the continuity implies like there can't be erected change, so limit x tends to 0 plus or 0 minus f dash x also exists, and that should be 0, right? So it means limit ipsa tends to 0 and this limit delta tends to 0, both will coincides, and that will definitely give an interval where 1 is guaranteed. So I hope this point is very clear to all of you. Let me show one more example of twice differentiability to give you a more feel. So from here what we can tell is, since f dash 0 is not 0, since f dash 0 is not 0, okay, so we are basically hunting for an open interval containing 0 in which f dash x never vanishes. But we know f dash given is continuous. F dash is a continuous function which I have discussed just now in great detail. Okay, so now from the mean value theorem we call like there is some delta greater than 0 such that f dash x is non-zero for all x belonging to minus delta to delta. Now this is a standard property of a continuous function, right? Because since f dash x is continuous, so imagine if I take psi x as f of f dash x, and if I take an interval x belonging to minus delta to delta. Now psi is a continuous function such that at x equal to 0 psi is dying, and if I take a small interval of minus delta to delta. Okay, so if it is positive at some point, is positive in sufficiently small neighborhood of that point. Similarly, if it is negative at some point, is negative in sufficiently a small neighborhood of that point. So that shows by way of theorem that because of continuity of f dash x, we can tell R to be minus S minus, so because of the continuity we can take R to be minus delta and S to be plus delta. Okay, and that shows the first part holds true. So that's a full justification. Of course it doesn't deserve 3 marks because many erroneous candidate who has not thought even 1% of this still would have ticked the option because its question was just about existence. Let's come to the second part of the question, and it's fairly simple because there exists some x naught from minus 4 to 4 such that mod of f dash x naught is less than equal to. So the existence part gives a hint for using Lagrange's mean value theorem. So for second part, we have an interval -4 to 0. In this interval, I'm going to apply straightforward Lagrange's mean value theorem. So we know f0 minus f of -4 by 0 minus -4 equal to some f dash x naught for some x naught. So there exists some x naught belonging to 0 to -4. This is directly from LMBT since function is continuous and is differentiable in this interval. So यहाँ से what we'll get is f0 minus f of 4 divided by 4 is equal to f dash x. So now if we'll take mod of this, that we give mod of that. All right. Now we know the maximum possible values of f0 that we can have because of codomain definition is 2. Similarly, f of 4 will also lie between -2 to +2. Okay, so f0 minus f4, it can lie from 4 to -4 because they are independently controlled. So you know when f0 is 2 and f4 is -2, it will come to 4 to -4. This you can say directly from triangle inequality as well, because I could have written f0 minus f of 4, difference of two sides less than sum of two sides of triangle, right? So this is anyway, maximum value is less than 2, so it's less than 4. So this quantity is definitely less than 4. So overall this quantity becomes less than 1. So that's very obvious. This you can feel graphically as well, because let's say you are moving in a span of 0 to -4 to 0, -4 to 0, and the maximum possible values that we can get is -2 to 2. Okay, so the maximum distance that I can height that I can travel is 4, and I have to move in a span of 4. So definitely the average speed, delta average speed, whatever you'll get, is 4 by 4 equal to 1. So there must be a time in your lifetime where instantaneous speed was also 1. This is directly from feel what fundamentally is mean value theorem I'm talking about. So second part was fairly easy, and that gives second is correct, first is correct. Third part is telling limit x tends to infinity, f of x equals 1. Now this part is wrong because we have only control about the initial value of the problem, right? We know the information at f of 0 and f dash of 0. It means we know only information about the value of function at 0 and its derivative at 0. So again, function is bounded by this. And now the slope of the function, even f dash 0 whole square is 85 minus f0 whole square, and this quantity can dance from 0 to 4 anyway, so it will dance from 9 to root 85. Okay, so we know anyway f dash 0 can go from 9. So let's say this is a line having slope 9, m equal to 9, and we have line having slope, let's say, root of 85. So whatever graph we are drawing, its slope will be sandwiched between them. So it can be shown to lie in this region, right? Now clearly we can draw the graph in such a fashion. That it can do anything later. So we don't care about what's happening here because the information is only supplied at x equal to 0. The graph might not start from origin. It can start from any point, but it can do anything crazily here. Like by making sure that the slope is between root 85 to 9. So slope will not be 0 as well. Okay, so from here you can see the information next what it will do. We don't have any control. In that sense, option C is wrong. Now if you want to justify it more, then actually you can divide the function. Because by looking at the problem f0 square plus f dash 0 square, it feels like something square plus its derivative square. And the most obvious function that hits you is sin square theta plus cos square theta, right? So if we'll try with the function sin x, f as sin x, clearly f dash will be cos x, and that doesn't satisfy this condition. Then maybe we can think of trying with f equal to 2 sin x, because our grid was, since the output of the function is going from -2 to 2. But again, f dash will give 2 cos x, and anyway at x equal to 0, 4 is not equal to 85. So that indeed doesn't satisfy. But still we can't lose our hope, and I can come with, let's say, some a sin cx, right? So that will give me f dash as AC cos cx. Yes or no? Or even if I take, let's say now I want f plus f dash square. So a square sin square cx plus c square cos square cx. This I want to be root 85. Means this I want to be 85 actually. Okay, so now there is many ways in which we can construct this. One such way is we can take a square as 85 and c to be 1, because if I'll take c1 I'll get sin square x plus cos square x as 1 and a is root 85. Okay, so we have a function root 85 sin x. With this function, if I'll differentiate, I'm going to be root 85 cos x, and you can clearly see f dash 0 plus f of 0 whole square is going to satisfy my boundary condition. So indeed I have found a function like this. Right? But now this function is clearly wrong function again. Why? Because the output of the function is from minus 2 to 2. So this will not satisfy the equation. It means I can't choose the amplitude to be more than 2. Okay, either you can make it a subset or not. Then again I can come, let's say suppose if I choose a as 1, and instead of this I choose an sin cx as a function and its derivative is c cos cx. I am just giving you from where this idea is coming, right? If you want to give a counter example. So now it is like sin square cx and f dash x square at 0 is basically c square, right? So that will give c square as 85. So that gives c equals root 85. If c is root 85, the function that I am getting is sin root 85x. So this indeed satisfies the condition, and you can see clearly limit x tends to infinity, this quantity will oscillate from minus 1 to 1, and hence again by that defense mechanism I can tell option 3 is wrong. Otherwise it was obvious. Now the most technical part of the question was, I think, the first option, which was loosely understood by most of the solver also, even by most of the faculties here unfortunately. And the fourth option, where there exists some alpha power minus 4 to 4, such that f plus f double dash alpha is 0 and f dash alpha is not 0. Okay, now possibly hint of this can come in two ways, because usually if we have problem like we have to show the existence of f alpha plus f double dash alpha equals 0 for some alpha from minus 4 to 4, will be tempted in this way, right? We can define a function usually fx plus f double dash x. We'll take this function as psi of x, and usually we try to apply the IVT, intermediate mean value theorem. So somehow at minus 4 and 4, at 4 if I know the value is positive, at minus 4 if I know value is negative, or vice versa. At 4 let's say is negative, minus 4 is positive, then I know there exists at least one point. There can be many points of course, but at least one point is guaranteed where it's 0. But unfortunately I don't have the value of function f of 4 and f double dash 4 information at 4. What I know is f of 4 will definitely be less than equal to 2, or to be more specific, mod f of 4 will be less than equal to 2. Okay, information about f double dash 0 is known, so we don't know information about f double dash 4 over here. So that stops me from this argument here. But we have some hope, because you can see the other way of applying Rolle's theorem is, okay, on the mother function I'll apply Rolle's theorem such that its derivative becomes this function. So basically we'll try to find a function whose derivative is f alpha plus f double dash alpha. That is very algebraic result of mean value theorem, and that's not very difficult to see from here, because even in the question itself options was hidden, because they wanted you to define something as square f square plus f dash x square, and indeed f square will give birth to f, and f dash will give birth to double derivative. So if I define a new function instead, psi x as f of x square, possibly with that hint, and that gives me psi dash x equals 2f dash fx plus 2f dash f double dash x. And now life is good over here, because in the problem they have already given, like we have to find and show actually existence, like there exists some alpha such that f dash alpha is non-zero but this quantity does. It means now I'll apply Holstrom on psi x. So what information I know? I know information at 0 because psi 0 is already 85, which is known to us. What else we know? We know from the previous psi is definitely a continuous function, because f is continuous and differentiable, so psi is continuous and heavily differentiable function. Okay, in psi 0 pe we know answer is 85. Now we also know the information at between 0 to minus 4, because between 0 to minus 4 we have seen from the second part of the problem, like there exists some x naught such that f dash x naught magnitude will be less than 1, right? And we also know f of x naught, no matter what x naught you take, its magnitude will be less than 2 from the codomain definition. So I can tell there exists some alpha between minus 4 to 0 such that f of alpha whole square plus f dash alpha whole square, this comes from Lagrange's theorem and this comes from codomain restriction, is less than equal to 5, right? तो आई नो लाइक कोई अल्फा के लिए इसका जो आउटपुट आएगा वो आउटपुट या तो 5 आएगा और 5 से लेस आएगा. एग्जैक्टली इन द सेम मैनर वी कैन टेक सम बीटा फ्रॉम 0 to 4, because you can see f of 4 minus f of 0 by 4 minus 0 equal to f dash beta by Lagrange's mean value theorem LMBT for some beta lying between 0 to 4. Now again from the codomain definition we know f of 4 minus f of 0 can go maximum to 4 and minimum to minus 4. So if I'll take mod on both sides, that again restricts mod of f dash beta is less than 1. And what about f beta? From codomain is less than 2. It means for beta also definitely the answer, the height that will give will be less than 5. So no matter what height you select, one thing is guaranteed, psi x is a continuous function. So it will take 3 points PQR into picture, and if any graph, continuous graph is going through these 3 points and differentiable, there exists at least 1 point in this interval. Okay, it has to pass to 85, so that is derivative is 0. It means there exists at least 1 point where psi dash must die. Now if psi dash will die, so either f dash will die or fx plus f double dash x will die. Now also, like f dash x can never be 0. Okay, so the only possibility is this will be 0. Why f dash x cannot be 0 for any point between alpha and beta? Because if f dash alpha becomes 0, so there exists some point between minus 4 to 4, the hypothesis of the problem. Hence, the answer for this problem in option D is there exists alpha for which f dash is not dying, and other consequences is definitely true. I hope you must have enjoyed the lecture.